more applications. All right. All right. Now sometimes a lot of people have questions here, so your questions might be absorbed here, but we'll see how this goes. First of all, well, we're going to talk about two categories. One is rectilinear motion. That's like dropping the brick on someone's foot. Okay. We're not throwing it like this because that's like two-dimensional, right? But dropping something on someone's foot. Or you could go like this, where you're only tracking the height. All right. Issue A: rectilinear motion. Okay, rectilinear motion. All right. Motion along the line. All right. Okay. So what's the idea here? All right. Here's the 0 point. So someone's stalking you. 0 is your place. All right. Okay. We have a particle, P, is your stalker's car, I guess. Okay. So P for more for particle points. This thing's moving. All right. Maybe I should put a T there. Right? Of T. But the position of this particle is given by S of T. S is a position function. Here it's on a horizontal axis, like west east. Right? And time T is in hours. It's a stopwatch, I guess. Time T is in hours. So maybe there's a policeman stalking a stalker. All right. Okay. Now remember our hierarchy here, our taxonomy. All right. S is for position. Okay, S of T, that represents position at time T. All right. What's the derivative of position? Velocity. Okay, so V of T, which is S prime of T, that's the velocity of the car at time T. Okay. One side note. Okay. The absolute value of velocity is called the what? On your car dashboard, you have a speedometer. Speed is never negative. Velocity can be, but speed is never negative. So just like here, distance is never negative, but position can be. Over here, speed is never negative, but velocity can be. Right. By the way, what's the derivative of velocity? Acceleration. A of t, which is v prime of t, which is s double prime of t. Right? That's acceleration. Okay. And the derivative of that is the jerk. I'm not kidding. All right. So you can call your enemy, you're a third derivative. All right. Okay, sample units. Okay, so position might be in miles, for example. Velocity might be in what? Miles per hour, maybe. Okay, same for speed. Okay. Acceleration might be miles per hour per hour. Okay. Like the gravitational constant for Earth, right? It's like what? Negative 32 feet per second, right? Or negative 9.8 meters per second. All right. That's negative. We'll talk about that. All right. Okay, example. Let's say we have a position function that looks like this. All right. S of t equals t cubed minus 9t squared minus 48t, okay, plus 1. Okay, so let's say that that's a position function, all right? Describe the motion of the particle. Okay, describe the motion of the particle on this time interval from -5 to 5 in hours. Okay, and here, it's okay for t to be negative. I mean, maybe t equals 0 is what, midnight? Maybe -5 is 7 p.m. maybe. All right, that's okay. Okay. So. Now, what you might be able to t against t, all right? But in a way, it's kind of awkward because we have to interpolate and extrapolate. Okay, there's a lot of guessing going on here. But what's a way of figuring out exactly what we know? How do you indicate what it is we know without having to present a bunch of guesses of how we interpolate and extrapolate? All right, so we're going to do a schematic of what this car is doing. Okay, first of all, let's find the velocity. The velocity function, okay, is given by the derivative of the position function with respect to t. Okay, velocity is the rate of change in position with respect to time. What's the derivative? Term by term. T cubed goes to 3t squared. Negative 9t squared goes to negative 18t. Negative 48t goes to negative 48. The plus 1, well, that tells you whether the person is at midnight, but it doesn't tell you about the rate of change. Okay, that dies. All right. Okay, so basically I'm looking for critical numbers here for S, all right? Bear in mind that S and V are both continuous on the open interval. Big Daddy S is continuous on the closed interval. And quite frankly, no, I'm not going to mark you off if you forget to mention these, but if you make note of that, great. Okay, we like the fact that these guys are good guys. Right, that's like a restricted domain over there. Okay, so what does the velocity function tell us about how this car is going? All right, let's do a sign chart again. We're going from t equals negative 5 to t equals positive 5. All right, and let's figure out what's going on here. Yeah, let's find the critical numbers first. All right, let's do that. So we know we're not D and E in here. Okay, we want to find CNs of S in the open interval. Okay, so we want to solve. Okay, this we want to find out where the derivative is. What number? 0. All right. So what does this equal 0? We have 3t squared minus 18t minus 48 equals 0. I can factor out a 3. T squared minus 6t minus 16 equals 0. Again, folks, you can go ahead and divide both sides by 3, but I like factoring because I like saying here's v of t, here's v of t, here's v of t, and you don't have the right to say that if you're multiplying and dividing by 3, for example, right? So I like retaining v of t on the left side in various forms. Turns out this does factor nicely over the integers. We have t minus 8, t plus 2. All right. So, set that equal to 0, we get t equals 8. Set that equal to 0, we get t equals negative 2. Question, are these both critical numbers? No.
Negative.
Just this guy. Why? What's wrong with that? Yeah. Okay, so 8 is not in, it's, okay, I'll say, what? Not in the open interval. Negative 5, 5. All right. So we take t equals negative 2. All right. So negative 2, that is in open negative 5, 5. We'll take him. So negative 2 is the only critical number for Big Daddy S. All right. So here's negative 2. Okay. That's our fence post there. All right. Let's deal with V. All right. Well, you could test values, or you can test values, or use this sort of sign method. Okay. But you're going to find that the velocity is going to be positive over here, negative over here. Again, you can either test values or you can analyze the signs of those factors. All right. Velocity is positive here, 0 here, negative over there. Now, what does that say about Big Daddy S? All right. Now, if my derivative is positive, I'm S, my derivative is V. If my derivative is positive, I'm doing what? Increasing. Okay. And if my derivative is negative, I'm decreasing. Now, we're traveling along a horizontal line. Okay? What does it mean if S is increasing? That means the car is going forward. Yeah, forward east to the right. Okay, the car is moving right. Moves to the right. Okay, or if you're talking about tossing up a ball, the ball is going up. Remember, right and up, east and north, they correspond to the positive directions. If S is decreasing, you're moving to the left. You're going west, or you're going down. If you're talking about the ball. Okay, so moving left. So what happens at time -2, 10 p.m.? The car's doing what?
Still.
Yeah, basically, it's reversing. Yeah, reversing direction. All right, questions? Questions? Okay, so keep that in mind. That's the significance of all that. All right. Now, questions? Questions? A lot of this is interpretive. What does it mean if something's positive, negative? All right. Now, what about the acceleration? All right. So A of t is, okay, let's take the derivative. 3t squared goes to 6t, negative 18t goes to negative 18. All right. And A is continuous on the open interval. A is continuous, therefore defined on the open interval. All right. Okay, to find the pins, all right, we're going to solve A of t equals 0. 6t minus 18 equals 0. Bottom line, t equals 3. 3 is good. 3 is in there, right? 3 is in the open interval. Okay, we like this guy. That's a pin. That's a pin for Big Daddy S, -3. Okay, that's like 9 p.m. Okay, questions about that? That calculation?
What's it negative? I'm sorry, that got me real quick here. So t equals 3.
Oh, that's not negative. That's not positive. All right, that's 3a. Okay, good. All right. T equals positive 3, so the pin is positive 3. That's 3a. All right. Questions? Questions? What does this mean? Okay, let's do it. From -5 to +5. Okay, t is our independent variable. 3 is our pin. Okay. Now, here's A, and here's V. Okay, before we used to put the Big Daddy down there. Now I just want to relate, a guy in its derivative, right? Before it was S and V, now it's V and A. All right, sign for A. Well, look here. This is easy. A is an increasing linear, right? We know it's negative here, then 0 here, then positive here. It's an increasing linear. You can test values also. All right. We have continuity throughout. All right. Continuity. Well, don't worry so much about the endpoints. All right. So, again, I'm V. My derivative is A. My derivative is negative, therefore I'm decreasing. Okay. If my derivative is positive, then I am increasing. Now the question is, well, so what? How do we interpret that? It's not as obvious as it might seem. I'm going to explain why right now. Question so far, by the way? Question? Yeah.
I thought the second derivative gave you concavity.
We're not worried about, you know what, I'm not thinking of it in the context of concavity of a graph. I'm thinking, practically speaking, what does this tell me? If acceleration is negative, velocity is decreasing. That's the practical. Actually, here we care more about that step by step, from one guy to his derivative. We don't worry so much about the second derivative yet.
Okay.
Now, here's a key question.
If the velocity over there is 0 at -2, and velocity is decreasing, how does that work out? Well,
Yeah, well, we're going to address that. Okay, so folks, think about this. So you're mad about a test score. You see me walking, you're walking around, all right? And you go up to the top of the building like King Kong, all right? textbook, you're going to drop it on my foot. All right? So you see me out here, right? You're going to drop the book. Question. When the book falls, okay, the position function is a height function. S of t is a height function. When the book falls, is the velocity increasing or decreasing? No.
The velocity.
Velocity. Now,
It has to increase at some point.
you're dropping, you're not going up. You're just dropping. All right, now, here's the thing. Here's the thing. What happens to the height of the book as it falls? It decreases. Okay, now, assuming we have differentiability, what sign is the derivative? Negative. So you agree, if the derivative is negative, the big guy is decreasing. All right? The velocity this way is negative. Now, how's it going to go? It's going to go something like negative 10 feet per second, negative 20 feet per second, negative 30 feet per second. You agree those numbers are decreasing. They're getting more negative. What is increasing? Not the velocity, but the speed, the absolute value. Okay, the speed's increasing. That's 10, 20, 30, right? Okay. And by the way, it changes linearly, right? Because the gravitational constant is a constant. Now, do you buy that? The speed increases, but the velocity decreases because it's getting more and more negative. Right? It's getting more and more negative. This is where a lot of people get confused. Here's the chart. Here's a key warning. All right. The velocity is positive versus the velocity is negative. All right. Then is the velocity increasing versus is the velocity decreasing? Okay, so I'm doing this all in terms of velocity. I'm focusing on the velocity. So what's the particle doing at any given time? Or precisely, it's on a neighborhood of value for t, but let's ignore the neighborhood thing. Right? Okay, bottom line. If the velocity is positive, then it's kind of common sense. It's obvious what's happening. All right. If the velocity is positive, that's like you're throwing something up, whether it's a ball or a missile. All right. Okay, if the velocity is positive, all right, if v is increasing, all right, then are we speeding up or slowing down? We're speeding up. That's like a missile, right? 10 miles per hour, 20 miles per hour, 30 miles per hour, right? Okay, so we're speeding up. What if velocity is decreasing? How about the car example, right? Well, let's say we're going 30 miles per hour, 20 miles per hour, 10 miles per hour. Are you speeding up or slowing down? Slowing down. So over here, if you go 10, 20, 30, that's speeding up. 10 miles per hour, 20 miles per hour, 30 miles per hour, you're speeding up. If you're going 30 miles per hour, 20, and then 10, you're slowing down, correct? Correct? If velocity is positive, it's obvious. When v is increasing, you're speeding up. If v is decreasing, you're slowing down. But what if v is negative? Okay, that's like that falling book example. All right. The falling book example, all right, if v is negative and decreasing, remember, that's like negative 10 miles per hour, negative 20 miles per hour, negative 30 miles per hour. Hopefully you're not throwing down the book that fast. You must be like Superman, but, or Superman. Okay? Is the book, you're super mad. Okay?
Is it because we're moving away from zero?
Yeah, that's right.
Okay.
Because speed measures how you're moving away from zero. Like that's right.
Exactly that.
Yeah, exactly. So speed is going 10, 20, 30. But velocity is going negative 10, negative 20. Are you speeding up or slowing down? Speeding up. The book's speeding up, right? Okay. And this way, if it's negative 30, negative 20, negative 10, okay, you're slowing down. Okay, that's like you're going west or left, okay? So the car's going in reverse and slowing down. Negative 30, negative 20, negative 10, it's slowing down, approaching zero. Remember, if you're approaching zero, you're slowing down. Okay, if your velocity is approaching zero, you're slowing down. So, bottom line, if velocity is positive, then the whole interpretation of velocity increasing versus decreasing, that's obvious. If velocity is negative, then it flips. You're in the twilight zone. Okay? Questions? Questions?
What determines where zero is? Like, I would think if I'm dropping a book off of a building, I'm at zero.
You're an endpoint. You're an endpoint. Your time is zero. That's a time t equals zero. Okay, so you're going. So okay, that's like this. You're dropping a book. This is like that. This is height versus time. At time zero, here's the height of the building, right? Height of building. That's your height.
Okay.
Okay, it goes like this. By the way, you don't visually see this. This is a t-axis, right? You don't visually see it. Okay.
So this isn't a distance thing, this is a, I don't even know what to call it.
Relative thing.
It's a matter of what the book is doing. What is it doing? What's the nature of its motion? How's it moving? That's the thing. How's it moving? Okay. Now here's the thing. Now at this point, at no point is the velocity zero, except arguably when you hit the ground. But when could it hit zero? If you do what? Lob it up. Because then how does it look? You lob it up, it reaches a maximum point, doesn't float off into space. And if it flows off into space, we're in trouble, right? Okay, and that's where the velocity is zero. Okay, and you agree, we might be interested in that because here it corresponds to a max point, the max point. Right? Okay, the derivative corresponds, the critical number corresponds to the vertex there. Okay, so the velocity is zero over there. All right, so what's happening to velocity? Here, down, down, down. It's negative all the way. Velocity is negative all the way through. Here, velocity is positive, then zero, then negative.
So it's getting more and more negative.
Yeah,
Because it's speeding up towards zero.
And why is that? Because the second derivative, that's g, little g for Earth, negative 32 feet per second per second. That's why g is negative. G is negative. Second derivative is negative. Therefore, first derivative is decreasing. A is negative, g is negative. Therefore, velocity is decreasing. That's why whenever you let something go or you lob it up, that's why velocity always decreases, because g is negative. G is A on Earth. Okay. The g for Earth is the acceleration constant for Earth. It's the gravitational constant acceleration for Earth. Negative 32 feet per second per second. Okay. A is negative. Therefore, v is decreasing. A is negative, so v is decreasing. Okay, whether you're talking about this or this, v is decreasing.
So the sign of the velocity is always going to be relative to where the ground is, essentially?
Well, no, it's how you're moving. Is your S
How do you move
increasing or
in relation
decreasing?
to the ground?
So let's say that the ground, it's not really a ground, right? Or maybe your thing burrows in there, right? It's not so much where the 0 point is, it's how you're moving. Okay, just like, look, the derivative of a constant is zero, right? We don't care what the milestones are saying. We care about motion. It's about the motion. Okay, so if v is increasing, your s value. Sorry. If v is positive, right? I'm s. This is v. If my derivative is positive, I'm increasing. Okay, I don't care if I'm going from 0 to 10 or from 1 million to 1 million 10. Right? Okay.
I just understand when velocity is smaller than zero for the chart, from the chart.
Yeah, I'm talking about velocity. That's the slopes.
Yeah.
Okay, h of t is s of t. Okay, height is position here. Okay, I'm graphing the position or height function here. Okay, the derivative is the slope, right? V is s prime, right?
Yeah.
Okay, what are the slopes here? What sign are they? They're negative, right? The slopes here are all negative. That means velocity is negative. Slopes here are positive. Velocity is positive. Slope here is zero. Velocity is zero, at least instantaneously, right? Slope here is negative. Velocity is negative.
So what if the velocity is increasing? When
Okay, now bear in mind that means that there's some you're actually like it's not just the Earth. Right? So it's like you're driving a car. You're driving a car.
yeah.
Okay, so it's not just a. So if you're driving a car, okay, if velocity is increasing, okay, if velocity is increasing, all right, then that'll be like this, for example, right? Okay. So the concave up effect. Yeah, it's related to concavity, right? Concave down, concave down. Okay, but notice in both cases, 20, 10, 0. Negative 10, negative 20, negative 30. Okay. So in both cases, velocity is decreasing. Here, velocity stays negative. Here, velocity changes sign from positive to 0 to negative. Like I said, a lot of your questions are going to be wrapped up in here. Questions? Okay. So in fact, we'll be done with part A, which means you can do part of 4.7. Okay, part B is economic. We can do that next time. So what does the schematic look like? All right. So what information do we have here? All right. So I'll do it this way. All right. So here's our t-axis. We have -5, +5. Okay. So what do we have here? What were our key values? Our key values were -2, which is a CN, and +3, which is a pin. Okay. All right. So what's going on here? What's going on here? All right. Well, first of all, just get an idea of where this thing is going. Okay. You might want to evaluate S of t for these various values. All right. So this. Okay. So what's S of -5? You just put it into Big Daddy S. That's -109. Okay. S of -2 is 53. S of 3 is -197. S of 5 is -339. Okay. Now our schematic is going to look like this. Leave a bunch of space here. Okay, our schematic's going to look like this. Okay, we're going to be graphing values for S of t, all right? And in fact, this is a one-dimensional line. This is just a simple number line here, right? It's like the street that your stalker is on. Okay, let's put some numbers here. Well, look at the numbers here, right? I mean, this person's going all the way from -339, what was that, miles? It's kind of weird, but off in the ocean. But okay, let's say this is -400, -300, -200, -100, 0, 100, and we can stop there. All right. Okay. So at time -5, that's 7 p.m., I guess. -109. Okay, that's over here. That's at time -5. Okay, that's one endpoint. All right. And then we have at time -2, we're at 53. Okay, we're at 53. Okay, that's fine. That's -2. All right. By the way, the reason why I'm not plotting on here is that I don't want to go like this. That'd be kind of stupid, right? So I'm kind of adding a second dimension just for visual clarity. Yeah.
Is it 53 or negative?
Is it positive or negative? It's positive. Positive, sorry. Okay, positive degree. All right. And then it looks like we're going left again. Right? In fact, remember we already determined that, right? We determined that that the car. Okay, these are like the windows again. Okay. Remember what we said before? We said before that the car was moving to the right up until time -2, and then to the left afterwards. Remember, we got that from before. That was that first sign chart I showed you. Okay? So we're going to the right. I'll put the arrow there to indicate we're moving to the right. Again, the vertical measure here has no meaning. Okay? The only reason why I'm throwing in a second dimension is that I don't want it to look stupid like this, where I'm just going like that, right? I got dumb. So I want to spread out the schematic. And then we turn around, so we actually do turn around here, all right? And we go left, okay? And then what do we do? Okay, so at time 3, we're at -197, and then we continue to the left, -339. That's a time +5 a.m. All right. So overall, now this is humble in the sense that it tells you without any interpolating or extrapolating, no guesswork, okay, aside from things like continuity, that we know that the car is moving to the right from this time to this time, and then it turns around and moves left. Okay. Now, what does the pin here tell us? All right. Well, number 3. okay, that number t equals 3 over there, all right, it tells us that the velocity, okay, is decreasing here, okay, and it's increasing over here. Now, if the car's, okay, now over here the velocity was positive, that's why the car moved to the right. Here it's negative, that's why the car moved to the left. Here it's negative, that's why the car moved to the left. Alright? So I'm looking at these pairs here. Okay, these pairs. If velocity is positive and decreasing, that's like 30 miles per hour, 20 miles per hour, 10 miles per hour. Is the car speeding up or slowing down? Slowing down. Okay, that makes sense, right? So we're slowing down from here to here. Alright? And then, okay, between -2 and okay, so between -2 and +3, so here, I'm slowing down. Now from time -2 to time 3, okay, 10 p.m. to 3 a.m. Velocity is negative and decreasing. Wait a minute, that means you're speeding up. Yeah, that's like a chart, right? You're speeding up. And then past 3 a.m., negative but increasing, hold it. Velocity is getting closer to 0. You're slowing down. All right. See that schematic? That gives us, assuming that we plotted these points exactly on the, corresponding numbers, this gives us exactly our state of information. Okay, assuming that I've corresponded these with the correct numbers here. All right. This gives me the exact state of play. I know exactly, when this thing's going to the right, going to the left, speeding up, slowing down. And we're not doing any inappropriate interpolations or extrapolations, which you would have done if you graphed S of t against t. You would have done a lot of guesswork. There's no guesswork here. It's a very humble graph. It's a very humble graph. It doesn't tell you exactly how position is changing with respect to time. It's very humble.